So let's try to solve this sample problem that we have here. So we have here a prop beam. Uh, we have a beam here that is fixed supported here and has a roller support here. So basically, this is what you call a prop beam. So it's like a cantilevered beam, but it just has a roller support here on the supposedly free end. Okay, so the question asks for the reactions of this prop beam. Okay, so as you can see here, we have drawn the free body diagram. The beam is loaded by a uniformly distributed load, 24 kilonewton per meter, and then at the fixed end at point A at joint A, since it is fixed supported, we know that the reactions or the number of unknowns at that particular joint uh, is composed of three reactions, mainly the vertical reaction, the horizontal reaction, and the moment reaction. So let us call them AY, AX, and MA respectively. While on the other end, on the roller support, let's call the restraint or the unknown reaction as BY. Okay, as you can see here, the rigidity EI is constant all over the length of the beam as given on the problem. And the length of the beam is 10 meters. Okay. So as you can see here, by just merely looking at the given structure, even if you don't know the formula for finding the determinacy of a beam, you can easily see on the given structure that it is actually indeterminate to the first degree. Simply because we have how many unknowns? One, two, three, four. We have four unknowns, but we only have three equations of equilibrium. So we have one unknown that we cannot solve. Okay. So basically, this structure is indeterminate to the first degree. Okay, but we will try to solve this structure. We will try to solve for the unknowns using the concept of method of consistent deformation or the force method. Actually, it's called force method because basically, uh, we are we are uh, we are trying to solve. We are trying to analyze the given structure by calculating the unknown forces. That's why it's called force method. There's another method of analyzing a structure, which is what we call the slope deflection method. So basically, that is somehow opposite of method of consistent deformation of force method because basically that method deals with displacement naman siya. Okay, that's why it's called slope deflection. Okay, so uh, by the concept of method of consistent deformation, as I've mentioned before, the response of the original given structure is just equal to the response of a primary structure and a structure loaded by the redundant. Okay, so as you can see here, at joint A, at point A, we have seen that the deflection of joint B, the vertical deflection of joint B, is actually zero. Obviously, because we have a roller support here. Okay? And we know for a fact that roller support restrains translation perpendicular to the surface kung saan siya naka-stand. Okay? It actually restrains motion or translation perpendicular to this direction. So therefore, walang deflection dyan along that direction. Same goes dito sa kabilang end, sa joint A. So since fixed support siya, it restrains translation along this direction, as well as yung rotation. Okay? Nagre-restrain din siya ng rotation kasi nga meron kang moment restraint dito. So therefore, yung slope nung beam at point A will obviously be equal to zero kasi nga nire-restrain ng fixed support, nire-restrain ng fixed support yung rotation at point A. Okay? So those are the actual response, or should I say actual characteristic of the given structure. Okay, so the first way or the first thing that we have to do if ever we want to apply method of consistent deformation on this structure is to choose a redundant. And how many redundants will we choose? Since we only have 1 degree of indeterminacy, therefore we only have to choose one redundant. Okay, we only have to choose one redundant. And again, you cannot choose a redundant as you wish. Okay, you have to consider the remaining structure after you have removed that particular redundant that you have chosen. Okay, so for this particular example, we can actually choose MA to be redundant simply because if ever we will remove that moment restraint here, the remaining structure will just be a simply supported beam with a hinge here on joint A simply because meron siyang AX tsaka AY reaction. So magiging simply supported lang siya. So determinate pa rin siya and stable. Take note, dapat stable pa rin siya after nyo i-remove yung redundant na pipiliin niya. Okay? But for the case of this particular example, I'd rather choose BY, redundant restraint to be my redundant. Okay? So again, applying the concept of force method or method of consistent deformation, since I have chosen By as my redundant, so I will just remove By from the whole structure. So the remaining structure will look something like this. Okay. So we just remove By, or in other words, we have removed the roller support at joint B. Okay, so the remaining structure will now just look like something like this. So the load will still remain, the external load, which has a magnitude of 24 kilonewton per meter. And if you will try to imagine what will be uh, the the elastic curve will look like, you can easily imagine that the elastic curve for this cantilever beam, again, after we have removed the roller support, the remaining primary determinate structure became a cantilever or cantilevered beam. Okay, with the free end at this joint. Okay, and since it is a cantilever beam, we can easily imagine the corresponding elastic curve that will result if ever we will load the cantilever beam with a 24 kilonewton per meter load. So the elastic curve will look something like this. So you can observe that this joint B, deflected from this initial position to this final position with a magnitude equal to, let's just call the magnitude of the deflection from this original position to this final position as delta B primary. Okay, meaning it is the deflection at joint B from the primary structure. This is what we call the primary structure. Primary structure. Okay. So after removing the redundant that we have chosen, uh, we will now try to apply that redundant to the resulting determinate structure as an external load. Okay, so the By here will be applied to this determinate structure as as an external load, which is this. Okay, so again, since that external load By is applied to this determinate structure, cantilevered structure, the cantilevered beam obviously will deflect in this manner. Okay, since we have applied the redundant By as an external load or external force. So you can see here, joint B, which is originally here, will move upward to this final position at with a magnitude of delta B redundant. So let us just call this amount of deflection as delta B redundant and this amount of deflection as delta B primary. Okay? So according to method of consistent deformation or force method, the response of this original given structure is just equal to the response of this primary structure plus the response of this determinate structure loaded by the redundant force. Okay, so in other words, the deflection, for example, the deflection at joint B, which is equal to 0, must be equal to the deflection at joint B on this primary structure plus the deflection at joint B from this determinate structure loaded by the redundant force. Or in equation form, I'll just try to convert that statement in equation form. So according to force method or method of consistent deformation, this response or this characteristic of the given original structure with the deflection equal to 0 at joint B must be equal to this deflection. Let us just give it a negative sign since it is moving downward. Equal to that deflection, let's call that delta B primary plus the deflection at the same joint due to the applied external redundant force By. So let us just call that delta B redundant. Delta B redundant. So basically, this is the working equation that we will try to work on. Okay, all of the things that we will employ in solving this particular sample problem will just revolve around on this particular equation, wherein the 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 deflection from the original actual structure must be equal to the sum of the deflection from the primary and the redundant structure or redundant loaded structure. Okay? So again guys, yung actual deflection dito hindi palaging zero 'yan. Okay? Sometimes there are questions na sinasabi merong settlement yung isang joint. For example, kunyari may sinabi yung joint B daw dito nagsettle ng 10 mm. Okay? So hindi na to zero. So dapat yung deflection nito tsaka nito magiging ano na, magiging equal to 10 mm na. Okay? Kung may sinabing nagse-settle yung joint B ng 10 mm Pero kung wala naman, we basically assume na zero yung deflection sa joint B. Okay? So to proceed, so you can see here na for us to be able to analyze this indeterminate structure, we have to deal with this equation, which involves computing the deflection of the primary structure, which is this, and the deflection of the structure loaded by the redundant force. Okay, so meaning for you to be able to use the method of consistent deformation or force method, you have to be able to compute for deflection, which is this. So we have different methods to compute deflection. Okay, we have uh, different methods to compute the deflection for a determinate structure like the 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 direct integration method or double integration method. We also have the area moment method. We also have the superposition method. We also have the conjugate beam method and uh, the work energy method such as the virtual work method and the Castellanos theorem or the partial derivative method. So we have several choices of methods to be used for us to be able to compute these two deflections that we have to compute here. But for this particular sample problem, I'd rather choose to use the virtual work method because for me, virtual work method for the computation of deflection is the most effective and most flexible method for me personally. I personally choose a virtual work method every time I compute deflection. So as you can remember, for you to be able to compute deflection using the virtual work method, you have to uh, memorize this very basic formula. Okay, wherein we already know the definition of each of the uh, terms that we can see here. M is just small m is just the moment equation from the from the structure loaded by a unit load, and then m is the moment equation from the given structure. E modulus of elasticity, I is the moment of inertia of the given structure. X1, X2 are just the limits for this moment equations. Okay, so let's start with the computation of the capital M of the bending moment. So let's try to cut the given structure. Let's try to solve this deflection first. Delta B primary. So since this is the primary structure, this is where we will compute for the bending moment, the capital M that we have here. So we have to cut the beam so as to compute for the moment equation. And again, every time you cut the beam, you have the freedom to choose whether you'll use this side or the left segment or this right segment. You have the freedom to choose, but for ease of computation, we will rather choose to use the right segment simply because we will just be dealing with this uniformly distributed load if we will be using the right segment. Unlike for the left segment, if we will try to use the left segment, we have to deal with the vertical, horizontal, and the moment reaction here. As well, in addition to this uniform distributed load. So might as well let's just use the right segment. So using the right segment, we put a cutting plane at a distance x from the right end, and then let's try to construct the moment equation. So we can see here uh, to construct the moment equation, we just simply get the moment of all of the forces to the right of this cutting section, which is just obviously the uniform distributed load only. So the uniform distributed load is the only load to the right of the right section. I mean, to the right of the cutting section. So we will just get the moment of this 20 kilonewton per meter uniform distributed load to this cutting plane. So we just need to get the resultant first of this uniform distributed load that we have here. So that is just a rectangle. So we just have to multiply the height, which is 24, to its length, which is equal to x. Okay, and then multiply it. So if this is the resultant, we just have to multiply it by its moment arm from the cutting section. So obviously, since it is just a rectangle, the moment arm is just equal to x over 2 or half of the length. And don't forget to include the sign negative simply because the uniform distributed load is pointing downward. That's why we have put the negative sign here. Okay, so basically that is the moment equation from the primary structure. Next is let us try to get the moment equation, the capital M, from the structure loaded by the redundant force. So the same as what we did here, we try to cut the beam using a cutting plane located at a certain distance x from the right end. So dapat parehas lang yung you must have the same reference point from your x from the x that you have used here and the x that you will use here. Okay, so they must have a the same reference point. Hindi pwede yung x mo dito nag-refer sa right end tas biglang yung x mo dito biglang dito naka-refer, so bawal yon. Bawal yung ganito, biglang dito na lang yung x naka-refer, naka-refer mo yung x dito. Bawal yan, dapat pareha sila ng reference point. Okay, so from this drawing, we can easily get the moment equation of the redundant force By. Let us just try to get its moment at this particular cutting section. So that moment will just be equal to force, which is By, times the perpendicular distance, which is x. And then the sign is positive simply because By is pointing upward. Okay, so these are the two moment equation that we need to compute primary deflection as well as the redundant deflection. So that is the capital M here. For the EI, we don't have to worry for the EI because aside from being constant, it will also just be cancelled later on, as you can see when we compute this final equation. The EI will just be cancelled, so we don't have to worry about that. Especially the left side of the equation is just 0, so it will just be cancelled out later on. But if ever we have a value here other than 0, that is the time that we have to give importance to the value of E and I, because they will significantly affect the result of your computation. Okay, so let's now move on to constructing the small m. The small m is just the moment equation from the structure loaded by a unit load. So we will just try to redraw the primary structure, and we will try to load it by a unit load. So when we say unit load, its magnitude is just equal to unity or equal to 1. So again, we will try to load the structure with a unit load with this direction. The direction of the unit load is actually arbitrary, but for simplicity of calculation, it will be our it will be our technique to just orient the unit load in the same direction as the direction of the redundant. Okay, so if the redundant is directed upward, the unit load that we will apply here will just have the same direction. That will just be the way we will use in our computation and in any other computation. They must have the same direction. But again, you can actually use the other way around. But again, for this particular sample problem, for 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 easiness of computation, we'll just orient the unit load on the same direction as the redundant. Okay, so since the redundant is directed upward, we will direct the unit load here upward as well. So if we will try to load the determinate structure with an upward unit load, the member will deflect in this manner, and as you can observe, this the same point here, point B, will move from this original position to this final position with a magnitude equal to delta V unit load. Okay, so for the construction of the small m, the moment equation from the unit load structure, again we will do the same thing. We will try to cut the structure with a cutting plane at a distance x, and then try to get the moment of all of the forces to the right of the cutting section. And obviously, only the unit load is the force to the right of the cutting section. So it is the only force that we will get the moment with respect to this cutting section. So the moment of the unit load to this cutting section is just equal to the magnitude of the load times its perpendicular distance, which is x. So that is simply the moment equation from the unit load structure. So after getting the capital and small m, it's now time to substitute them to this equation to solve for the deflection at B. Okay, so let's try to solve first for the deflection at B primary. So deflection B primary is just equal to integral of small m, which is this, times capital M, which is this, for the primary structure. So that is just negative 24x x over 2 over EI times dx over EI times dx. Limits from x1 to x2. So as we can see here, our limit is starting from this 0, 0 point to this final point here with a magnitude equal to 10 meters. You just have to be careful with the consistency of your units. Make sure that your units will be consistent. Although for this particular example, since the load is in terms of kilonewton per meter as well as the distance are in meters, so I suppose our units will just be consistent. Okay, So solving for this integral using your calculator, the answer will be equal to this negative 30,000 over EI. So we can see here the EI will just be a variable, or I mean the EI will just remain because it is constant. We can move it outside of the integral sign. So the answer will be negative 30,000 over EI. So you can see here, there is a negative sign for the deflection of the primary structure. So what does it mean? It just simply means that our direction for the unit load is not the same as the deflection of the primary structure. Or in other words, we have put a wrong direction of the unit load for the primary structure. As you can remember from the virtual work method, the direction of the unit load that we have here must be directed in the same direction as the assumed direction of the deflection. But as what we did here, since we are adapting the direction of the redundantly loaded structure instead of the primary structure, so it will obviously be directed on the opposite direction as the primary structure. That's why we have a negative sign here. That is the only meaning of that negative sign. Okay, but if we will try to direct this, or should I say, if we will try to construct another another structure with the correct direction like this one, if we will try to construct a structure with the same direction as the primary structure, we can easily see that the moment equation for that will just be equal to negative 1 times x. So you can see here, if this will be negative, the negative here and the negative here will just cancel out. So it will just show that our unit load structure has the same direction, or I mean the unit load that we have here on our structure has the same direction as our primary primary deflection, which is the case for the virtual work method. But then again, just to uh, just to prevent us from having so many drawings, instead of drawing this, or I mean, instead of having another drawing for the unit load for the primary structure, might as well we just use the unit load structure for the redundant for solving the primary. Okay, but in a if you will just if you just want to have a long method or long solution, you have to construct a separate unit loads. I mean, you just have to construct a structure loaded by a unit load separately for this structure and then for this structure. So you'll have uh, two structures loaded by a unit load, one for the primary and one for the redundant. Okay. But again, for this particular example, we have used a technique just to minimize the amount of computation and drawing required. We just use the 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 structure loaded by a unit load for the redundant in computing the deflection for the primary structure. Okay, but again, the result will still be fine. It's okay to have a negative sign. It will just indicate that the direction of this unit load is not the same as the primary structure. That is that will just be the only meaning for that particular negative sign. Okay, so that is the basically of the that is the magnitude of the primary deflection, 30,000 over EI. If you have a value of EI, you can substitute that here to get the actual deflection. But then again, for this particular example, it is not recommended to actually solve for EI, because later on, as you can see, it will just cancel out. Okay, so since we are now finished with the primary deflection, let's now move on to the redundant deflection. Same formula, we'll still use this formula. Small m will still have the same value, 1x. EI will have the same value. the only thing that will change here is the value of the capital M, because it will now be byx. Okay, so the by and the ei here, which are constant, can be moved outside the integral sign. Okay, so if we will try to simplify the integral sign, the result will just be equal to 1000 over 3, and then let's put back the by over ei that we have removed a while ago. So this will be the value of the deflection of the redundant of the structure loaded by the redundant force. Okay, so since we already computed the value of delta B primary and delta B redundant, it's now time to go back to our original equation a while ago, wherein we said that the sum of the primary deflection, I mean the sum of the deflection from the primary structure, and the sum and the magnitude of the deflection from the structure loaded by the redundant force must be equal to the actual deflection. Okay, or in equation form, the the magnitude of the deflection from the primary structure, which is equal to 30,000 over ei. We just put a negative sign here to indicate that delta B primary and delta B redundant have different direction, which is obvious on the drawing. Okay, uh, so the sum of the primary deflection and the redundant deflection, which is this, must be equal to the actual deflection, which is equal to 0. Okay, so this will be our equation, and as you can see here, the ei can be cancelled if we will try to multiply the whole equation by ei. Ei cancel, ei cancel, ei times 0, 0. Okay, so the only unknown on this equation will just be by. Solving for by, we can see that by is just equal to 90 kilonewton. So that is the magnitude of the reaction on this support from the actual given structure. So by is just equal to 90 kilonewton. So after solving for by by using statics, you can easily solve for the other unknowns here, for ay, ax, and for ma. Okay, so I'll just leave that up to you as a practice. So try to solve the other reaction. You can already solve for the other reactions because there are only three unknowns remaining here, because by is already computed by method of consistent deformation or force method. So basically, that is how you apply method of consistent deformation or force method in solving or analyzing indeterminate beams. So this is an indeterminate beam. And actually you will do the same thing if you will try to apply method of consistent deformation or force method in analyzing an indeterminate frame. Okay, same method, same thing, same concept will be used for the analysis of indeterminate frames. Okay, so that will be uh, that is not the final answer here, because the question asks for the reaction. So you have to solve to you also have to solve for ax, ay, and ma. And then after solving the all of the unknowns, you can actually check if your answers are correct by checking the the equilibrium of the whole structure. You can try to sum up forces along the vertical direction or horizontal direction, as well as moments, and their values must be equal to 0, so as to make the given structure uh, 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 in equilibrium. Okay, so if you will try to solve for all of the unknowns here, you can easily see that the vertical reaction at joint A is equal to 150. The moment is 300. AX just equal to 0, which is obvious. Obviously, AX is equal to 0 because there is no horizontal applied force here to be resisted by the horizontal component of the fixed support. Okay, so basically, this is the final answer for this particular problem.